So the curve K, note, is going to be what? It is a circle centered at I with a small enough radius R so that K is inside C. Okay. All right, if we go back to the picture, for those the observant people in the, let me make that arrow look a little bit better. For the observant people in the crowd, you know that, oh, I can choose the radius to be 1 here. Now, I want to stress that it does not matter the size of the radius, because, again, we're about to generalize this once we complete this. All right, but you can choose the radius small enough so that it remains inside C. All right, so we need to parameterize this if we want to actually, compute some integrals. And how does that look? All right, well, so take your circle, which is cosine plus I sine, scale it down so we get the right radius, so r times all of that. So you'll have your r cosine t plus I r sine of t. And then now we need to shift it so that it's centered at I. And the way we will accomplish that is by shifting it up by I, so add in I. And there we go. Beautiful. All right, so that is the parameterization, and of course this piece right here, if you really wanted to have it in its real and imaginary parts, you absolutely can do that. Like that. Beautiful. Okay. All right, now what? All right, well, now what is, okay, in order to pop this into my integral, I need to take its derivative and plug in the dz for that, and then plug in the parameterization for z, and clean it all up. All right, now if I do that, let's compute the dz. The derivative of this is business as usual, because, right, again, the derivative is with respect to t, so I'll pick up negative r sine, and here I'll pick up plus I r cosine, and I has nothing to do with t, so it's gone. So we'll have negative r sine of t plus I r cosine of t. Okay, and then now, here's where we're going to pull a little bit of a sneaky, because we're now going to go to our integral, our curve k, z minus 1i dz. All right, and what are we going to do here? Okay, well, the first thing we need to deal with, of course, is the 1 over I. So let's look at 1 over z minus I. So we pop in the parameterization for z, and now note that's this. So z minus I is actually just going to be r cosine of t plus I r sine of t. And now note that that would be 1 over r e to the it. Reet. Right, because you can factor out the r, and then you've got cosine plus I sine t, so we know what that's equal to. Okay. Now, the dz, note we got a nice expression for that, but the dz, if we look at it ever so carefully, if you factor r and I out, you'll get cosine of t and plus I sine of t right there. Right, multiply the ri throughout. You'll get ri times cosine t right there, and I times I is negative 1. So the dz is actually ri e to the it. Beautiful. So when I pop all of this into my integral then, the parameterization is from 0 to 2 pi because it's a circle. 1 over z minus I, we have just justified, needs to equal 1 over r e to the it. dz we've justified is ri e to the it dt. Well, yeah, let me make sure I forgot my dt's. So dt. And now what happens? Well, r is a radius of a circle, so it's positive, so those delete each other. E to the it, e divided by e to the it is equal to 1. And I can get pulled out of the integral. And there we go. Beautiful. We have done the computation. And as promised, it's 2 pi I. Hooray! So, now I did this with a radius r to stress something. The size of the circle does not matter, right? Note, the radius will show up and delete itself. So, everything we did here, does it matter that I had a minus I in the bottom? No, right? Pick any complex number there, and then you just shift the circle to make sure it lands there. The curve C here was just some square, and note that I was always able to squeeze a little circle inside, because a simple closed curve will always enclose an area, and I can always sneak a circle inside of there, right? It's always going to enclose an open set. Right, it's always going to have an inside. So, with that said, the punchline here now for this wonderful work that we did here any integral that looks like this where C is a simple closed curve that encloses the complex number alpha, this will always come out to 2 pi I, no matter what you do. So now we know that if you want to integrate 1 over z minus alpha, you can always do it. It is always possible to compute this, and you will always get 2 pi I, as long as the curve C encloses alpha. If it doesn't enclose alpha, then we know it's equal to 0 by Cauchy-Grassat. But now Cauchy-Grassat told me how to compute this one. So, hey, beautiful. All right, and before we move on, I would like to note this works for multiple curves as well. So now that we know how to compute this, and it's always 2 pi I, we can actually continue going this process and do it for multiple curves. So, more facts. So, let's look at a specific example of this and see it in action. So, for example, suppose we would like to compute the following. 1 over z squared minus 1 dz. Ooh, note, 1 over z squared minus 1 has 2 spots where it's not happy, 1 and minus 1. It'd be awful if C enclosed both of those. Oh, aren't I a jerk? Okay. So, what do we do here now? So, the trick we pulled to actually get Cauchy-Grassat to apply, and then allow us to do some nice integrals using that deformation of curve principle, we had to introduce a closed curve inside of our original closed one to make everything work out. Now, for this one here, here's how it's going to look. Note that z squared minus 1 equals 0, and this is still exactly what you think it should be, plus or minus 1. There's nothing else. Nothing weird happens. This is 2 roots. Okay, and if we go to our picture, so we have 1, we have minus 1, and our curve C is right here. So my function 1 over z has 2 spots where it fails to be analytic, and so the trick ends up being to do a k1 here and a k2 here. And it turns out that the integral on C will actually equal the sum of the integral on k1 and the integral on k2. So it turns out by using the same trick that we did before where you kind of create some line segments and glue everything together, you can do it for more than one curve. And what you'll get is that this will actually equal whatever the integral on k1 will be, plus whatever the integral on k2 will be. So by doing the same argument where you connect things with line segments and then you break them into parts and get Cauchy-Grassat, you can work out the details. It doesn't work for just one curve. If you have multiple curves, you can pull off the same trick. So the question now becomes, though, well, how do we deal with the integral of 1 over z squared minus 1 on both k1 and on k2 here? Okay, so the way to handle it is to, of course, note that, well, 1 over z squared minus 1, I can partial fractions that now, can't I? In particular, partial fractions out to this. So, if I wanted to, say, do the integral of k1 of 1 over z squared minus 1 dz, all right, and as we noted, integrals split up the way you think they should. I am trying to draw a circle before I draw the integral, so let me get that going. K2, 1 over z plus 1 dz. All right, so on K1, note, K1 is enclosing z equals 1. And it's excluding negative 1. Note how I chose it. Okay, so on K1, why did that turn the K2 down there? I don't know. On K1, this thing will integrate to 2 pi I. And on K1, this thing will integrate out to 0, because K1, it does not enclose where this thing is not analytic. So by Cauchy-Grassat, this part is equal to 0. So here we'll pick up a... Yeah, let's just go to the next page. So the top one we know has to be 2 pi I, because we did the work for that. And the other one we know has to equal 0 by Cauchy-Grassat. So I pick up a pi I. All right. And similarly, if I integrate my function z squared minus 1 dz on k2, this is really the integral on k2 of 1 over z minus 1 dz minus 1/2 the integral of k2 plus. Now this time on k2 encloses negative 1 and excludes 1. So on k2, the first integral will 0 out by Cauchy-Grassat, but the next one will have to be 2 pi I by the work we did. And so we know we will get negative pi I for this integral. And so putting it all together then tells me that my original integral conveniently actually equals 0. Well, isn't that cool? So that's kind of a neat fact on this one here. So this will have to be pi I minus pi I, and that will give me 0. Pretty cool. All right. And there we go. So there we see some wonderful little applications of Cauchy-Grassat. Pretty cool. All right. So